Good morning, everyone. Early in the morning.
Morning, Doug.
Hi, Dale. How are you today?
Doing okay. It's still way too early to be up, but I'm here.
It's painful, I know. Very painful. Well, let's see. I had a few of you ask me about this question in the assignment, and I think it would be good for us to play with it, all of us, just for a minute, even if you got it right. See if my machine will wake up. Oh yeah, baby. And I guess I just want to, I don't know. And I hope we, when we review for the test in this section, we'll have a little bit more time here too. But I'm very interested that you just kind of slow down with these questions, really do a good job drawing pictures and so forth so that you can visualize what you're doing. So this is, a few of you asked me about 6.3, number 14, because it's just such a nasty question. Again, I mentioned in class that I'm not going to give you any questions where you're rotating it around some other axis than the X or Y axis, because it just seems like cruel and unusual punishment. But if you draw pictures of it, you still can get these ridiculous things correct. So let's see, if we're spinning this thing around the Y equals 4 axis, this was one of your, all of your questions were similar to this. I think this was Thomas's question, but so if it spins around that axis, then I'm talking about this shape. It said defined by that space down there, and then it's going to spin around that line. So that means it's going to kind of land up here someplace. Let's see. Guess I'll just make maybe a fairly terrible drawing of it. So it's going to spin. I'm going to probably erase that, but it's going to kind of spin. It's a terrible drawing. Spin around that axis and create kind of an, I don't know, an inner tube looking sort of a shape. But let's see if we can't draw a little bit better what's going on here. So the important thing is really just to picture that if I take a slice of this, right here, and I spin it around that axis, that means it's going to kind of bang up here someplace. What I'm really looking for is kind of that disc, that, let's see, let me think about this for a second. So it's hard to draw these. And maybe I'll leave it like that. Struggling. That's not my A game, that's for sure. Really just the question though, if I kind of maybe draw it off to the side over here. Really the question in every one of these cases is, do you see the cylinder kind of, do you see the cylinder that's drawn there? So the main thing is figuring out the two radiuses So in the end, what I really need is this radius out here. So in my mind, the whole thing is based on the picture. That radius right there, that's the outer radius. So maybe I'll call it RO for radius outer. And then this distance to here is radius inner. It's really those two that I'm working on. And since this thickness right here is dx, since it's going horizontal in the x direction, then really what that tells me is, okay, cylinder, outer cylinder. So my outer cylinder area or volume is equal to pi times its radius, radius outer squared times its height, which in this case, its height is dx. I mean, do you see that? If I redraw this over here on the side, a little bit larger. Do you see that as that outer shape? So it's going from the green line all the way up to where it hits on the axis or on the kind of the red curve. So that's its radius. And then because this has a hole in it, really what I'm doing is coming in and saying, oh, okay, well then I'm going to have to subtract off the inner cylinder. Well, this is the same thing. Its volume is equal though to pi times the, well, whatever the inner radius is squared times its height. But this problem is just so nasty because, you know, what is it how do I actually kind of draw that all out? So it is literally just cylinders that you're adding up. And again, we got to let this cylinder slide its way all the way to this side. And as it slides, its outer radius is going to get taller. As I slide that to the left, you see the outer radius is getting taller. Whereas notice the inner radius is going to follow that line right there. The inner radius actually isn't going to change. So that's why I've got to add these all up as they slide along. So I'm thinking, okay, great. Well, then that's the integral of this statement right here. Minus the other one. I guess I'm just curious, are you seeing that okay? I mean, that's very hard if you're not drawing it and so forth. But even if you can't make a decent 3D drawing, which I can't either, apparently, it's hard to do. Can you at least see the slice? Can you at least see where the slice is sitting in there? Well, now all I have to do is recognize that I'm kind of sort of stuck in X land. I've got to work with X's. So I really need those R's to be X's somehow. And if I go back over to my drawing, does it make sense to you that that R0, well, what do I get out of this? Unfortunately, what I really get is, well, only that distance right there. Like that distance right there is like the Y coordinate. That's the Y coordinate on that X to the 6th graph. And so if I want this radius here, because the distance, thanks to this picture, because the distance up there is 4, then doesn't that mean R0 would be equal to 4 minus whatever that Y is? I can't see this unless I draw this picture. I mean, I'm saying I can't see this unless I draw this picture. Again, if we spin this around the x-axis, we don't have this problem because that Y value right there is the radius and it isn't that hard. But in this case, I really got to draw pictures. So then, okay, that larger radius, R outer, is 4 minus the Y value of my X to the 6th graph. Well, this is how I get into X land. Because I know that Y on that is the same as X to the 6th, then I can say, okay, well, cool. That means R is 4 minus X to the 6th. And so then I can throw that statement in instead of R0, instead of R outer. Cool. Now I just have x's. So, and again, I think it helps to kind of picture this. So I've got 4 minus x to the 6th, and then, ooh, that's squared, not good. But at least it's all x's. What about that inner radius? Well, notice that inner radius is the distance from 4 to 1. In other words, in this case, it's just 3. Like as I slide it along, it's not changing. It's just 3 the whole time. No matter where I slide that distance is 3. Cool. R1 is 3. Oh, okay, great. Then I replace this with pi times 3 squared dx. and then I'm on my way. The question is, can I take that integral? Do I have to cheat to take that integral? Based on the questions that you're doing, they're takeable. Like you can actually square. You can square 4 minus x to the 6th out, and then you don't have a function inside of a function. They both have a pi, or you can pull the pi out of both of them if you want to. There's all kinds of things that you can do. I'll at least write one step in, just maybe one step in this because I won't complete it. But if I pulled the pi out and then I square this, 4 minus x to the 6th squared just means this, as you know. And so I'm going to go 4 times 4, which is 16, minus 4x to the 6th minus another 4x to the 6th is minus 8x to the 6th, and x to the 6th times x to the 6th would be x to the 12th. And then I still have that minus 9. So all of a sudden this looks pretty doable. Of course, I could collect that 9 and that 16 together if I wanted to, and then that's just a power rule problem. But the hard part of this stuff is drawing the picture. Does that make sense? I mean, I think if you don't draw the picture, you're not going to get these questions right. At least I can't. Maybe you have better vision with this stuff than I do. And as I said, this question's even worse because you're not even rotating it around one of the axes, but you really got to draw that stuff out to see it. And I would encourage you to, stay after. Let's talk about it more. This takes a lot of practice. When it clicks, you'll go, okay, I can do this. But until it clicks, it's kind of hard. At least I remember finding it hard. So I guess my only advice would be, again, there's all kinds of odd questions in the book, odd because they have the answers in the back, although you don't, in a sense, need that because yeah, you do. It's nice to have the right answer is the point. But spend your attention in just trying to set these things up. And I guess personally, I kind of like this just because I can really see the two cylinders. I can see the pi r squared h minus pi r squared h. I can see the cylinders. As soon as you scramble it around and so forth, and as soon as I get here, I'm taking an integral now, but I've kind of lost the vision of, oh, this is just one cylinder minus another. That's not terrible.
So Doug, I ran into the homework where it kind of started wanting us to just like multiply. So it was like 4 minus x to the 6th multiplied by, 3 squared or something. I just remember not being able to have that vision. And I wondered what multiplication meant instead of like adding and subtracting.
Well, like this problem, because you're doing it using the disc method or the washer method, because in the end, that shape right there, looks like a washer. In that case, and one of the things people confuse is notice you have junk squared. You have junk squared minus junk squared. That's very different than 4 minus x to the 6th minus 3 and then squaring it, like squaring it later. Like that's not true. That's not the same thing. But then of course you mix this up with the concept of shells, and in shells you are multiplying by something. I mean, I think that's what you're getting at, Connor. I'm not sure, but
yeah, I think I am getting a little confused between washers and shells. They're kind of similar in my head.
Yeah, well, and that's kind of what I mean. I think that's why the picture drawing is sort of worth 1,000. So let's just set up a quick kind of a shell sort of a question, and I'll, instead of rotating around let's see how we're going to do this.
Well, can you do the one we just did with shells, or is shells only for a specific? Because I feel like we're kind of arbitrarily doing shells and washers. Like I can't figure out when to
Yeah,
do which.
let's try that. That's not a bad idea. Let's try to do the one we just did with shells. Let's see. At least let's set it up. The question is always kind of like and I guess what I'd like you to think big picture, because, and again, there's just maybe nerd bonus points for being able to take that integral and get the exact answer. But the real question is, if you can set the dumb thing up, then you can let technology tell you the answer, and now you got an approximate volume. And so that's kind of the key. So, setting it up is really the part that matters in the real world. So let's try visualizing this with shells and see if we can make any headway with that. So shells is where you slice it the other direction. You have no choice in that last problem but to slice it, if you will, vertically, which made dx. And so shells is where you say, no, let's actually slice it horizontally like this. And now I'm going to spin that shell around x equals 4. So the concept behind shells is where you sort of think of that as sliced open, chopped open. And so now this thing is laid out like this, all stretched out. So the question is, how tall is that? How long is it across here? And then how thick is it? So notice in this case, its thickness is a little bit of y, like its thickness is dy. And its length would be the circumference of the circle, which is 2 times pi times radius, or pi times diameter, whichever way you want to look at that. And then its height, of course, would be, that distance right there. That's its height. So now I just got to look at the picture and say, well, can I figure out what that is? Well, that height isn't that height kind of the x coordinate of the red curve, whatever x is? Okay, so great. And then 2 times pi times radius. Well, that radius is the same thing that we saw a minute ago. In other words, that radius right there is 4 minus the y coordinate of the red curve. Again, please stop me and say, explain, or I don't get why you said that. So in this form right here, the volume is just all these things, because it's really kind of a box. It's really just dy, doesn't matter what order, dy times h times the circumference. So then I'm saying, okay, great. Well, in our case then, if I switch out some stuff, I've got dy, fine. I've got h, which we said was the same as x. Again, do you see that? X of the red curve. And then I've got the circumference, which is 2 times pi times radius, except for we said, hey, radius is 4 minus y. And again, this kind of insinuates that I'm stuck with y. Now, with respect to where this little slice that I made lives here, what y values And again, we're talking about the red curve since everything pertained to the red curve here. But what y values does that, where does that slice slide? What y values does it slide from?
From 0 to 1.
Yeah, I'm thinking it tops out here and bottoms out there. So isn't that 0 to 1? Now, in my case, notice I'm sliding this thing around and I'm sort of visualizing it as just this right-hand side. Now, really, the slice actually goes all the way over to here, doesn't it? But since it's symmetrical, in my case, I'm just thinking, oh, I'll just slide it from 0 to 1 and double it, or can I do that? Well, does it make sense in my case, since I just said, hey, this distance right here is X, and that's all I'm going to worry about, then I would have to double that. So my height would really be two X's. Do you see what I'm saying? And I didn't notice that. I'm like, because of the picture, I realized, oh, yeah, that's right. I got to think about that a little bit more. So the height is really equal to 2 X's. So let's get that in there. And so, yeah, this really lives from 1 to 0. So now, and the concept of throwing this summation symbol in here is because you're saying, hey, I just defined that little slice right there, and I'm going to slide it around. But I got to let it be everything from 0 to 1. And when I slide it up, then that height is going to get taller. When I slide it down, that height is going to get shorter. And I got to get all of those. So that's why I'm adding them all up. So I've got a dy here, I've got a 2x, and I've got a 2 pi and a 4 minus y. And so I'm ready to rip, except for I've got that x there. Well, how am I going to get rid of that x? Well, again, that's this conversion is what allows me to go back between these two worlds. And so if y is x to the 1/6 or the 6th power, then that means x would be equal to y to the 1/6 power if I raise both sides to the 1/6 power, or you could say that's the 6th root of y. That's what x would be. And then if you want to, you can say, hey, look at all these constants, 2 times 2 times pi. In other words, there's a 4 pi out front that I'll ignore till later. And that x is the 6th root of y. And I have a 4 minus y.
That makes way more sense. I think during the homework, I started kind of getting lost in the algebra rather than trying to picture it.
Yeah, the key to this stuff is you can picture this stuff. I remember being confused by this too. Like if you're not confused, good for you. Like I'm really impressed. Like you should be, this should hurt. There should be smoke coming out your ears. But in my opinion, you've got no chance of getting this right unless you draw a picture of it and literally slow down and, you know, like I did back here, draw the radius in, draw the height and see it all happening before your eyes. If you can't do that, then it's just so hard to make sense of this stuff. So yeah, you can actually do this both ways. And, you know, the question just becomes, you know, now that I'm sitting here ready to take this integral, notice that blue integral is really takeable. That's a really straightforward integral to take. Whereas I'm staring at the one we just made and I'm thinking, oh boy, that doesn't look good. Wait a minute. Yeah, it does. That's easy. Why is that easy?
So you can change the y to the 6th root to just y to the 1/6.
Right, and then I could actually distribute it in. So actually, when I put a box around that and said I'm done, it's because my gut instinct was, oh, that's going to be terrible, because we don't like multiplication in integral land. But you know, we can actually multiply it out, and so 4 times y to the 1/6. Y to the 1/6 times y to the first, you add exponents, so that'd be y to the 7/6. So I should get the same answer for both those integrals, and they're both takeable. Like I can actually take them. That's amazing. Now, I don't think I've made any mistakes because I went really slow, but if I, you know, go answer both of these problems and I get the same answer, I'm going to be really surprised and happy because there's just a lot of things you can draw wrong or misconceive, leave out a 2 like I was doing with the height and so forth. So, I don't want to take the time to do both of these from here, but I'm hoping those are the same answer. So what I'm going to do on the test is, number one, we're never, as I said, going to go around a weird axis. But number two, I'm going to try to give you a drawing of it, like the best I can do to help you draw it, because it takes some talent. And some of you are artistic and way better at this than me. One of our teachers is a really good artist, and his especially when you go 3-dimensional with this stuff, his ability to help you visualize it is much better than mine is. But I'm not terrible. Some of you are worse than me, and that makes it even harder. And so at very least, just draw a slice of it, even if it's not a 3-dimensional looking. This drawing isn't bad right here. That's not bad. That at least I can see the cylinder. I can see the shell sliding around the outside. So it helps me be able to draw in the radius and so forth. But my guess is you need more practice with this. So, take the time to do it. You got book problems and actually just don't even worry about taking the integral. Just try to set it up in both ways and then cheat on the calculator and see if you can get it to produce the same decimal answer. In that sense, you don't need to have an answer to check it. But, there's 6.3 and 6.4 odd questions that are in the back of the book. So, do some of those. Stay after class. Let's talk about it. I'm grading the bead project right now. I'm like a third of the way through. So I've responded to some of you that your last name is higher in the alphabet. So I think I'll wait and talk about that tomorrow after I've graded everybody, just to see how people did. Okay. So fortunately we have something kind of easy today, which is good. We need a chill pill here a little bit. But this is just something that is so cool. And it illustrates the beauty of like what math can do and what algebra can do and so forth. But the concept is basically this. Maybe you know this, but if I took a rock, and tomorrow's project is going to deal with this concept, but if I take a rock and I throw it in the air, kind of flies through there like this, and maybe it goes down and lands on the ground over here. What shape is that flying in?
A parabola.
Yeah, that actually follows the shape of a parabola. Would you agree that one of the interesting questions about this, and tomorrow is going to be one of the an actual reason for this, but one of the interesting questions is kind of the distance that travels. I mean, in a XY distance, it travels a certain distance in Y and a certain distance in X and kind of heads over there. But isn't it kind of interesting to wonder, could we actually get literally the length from, well, I guess I'll say A to B. How far is it? How far does that rock actually kind of fly through the air? What is the length of that curve?
Wouldn't that just be the integral of the curve from A to B?
Yes, except for that give you the area under the curve. They give you something totally different. Well, here's the issue. We got to come up with some way to kind of conceptualize that, and I'll show you what it is. So let me just draw like a chunk of a curve right here. And so if we went from, and this is what integrals really do. Remember, integrals add up lots of little stuff. Well, if I went from here to here, does it make sense when you zoom in on it? Even though that's a curve, that little chunk of it's a straight line. Well, straight-ish, as long as the 2 points are really close together. Remember, calculus isn't afraid of 2 points being infinitely close. So if those are really close together, isn't that a straight line? How do you find the distance of something like that when it's kind of sitting there at an angle? Anybody have any gut reaction about that? If I wanted to find that distance, how would I do it?
You treat it as though it's the hypotenuse of a triangle.
That's exactly right. You treat it as though it's the hypotenuse of a right triangle. So let's do that. Let's draw in that little right triangle. So if I knew those two lengths, couldn't I square them, add them together and square root it? And then I would have the hypotenuse of the triangle, Pythagorean theorem. Now, again, for this to work, those 2 points have to be really close, right? It's not fair to say that thing is straight if those 2 points are very far apart, right? If I go back to my picture over here and I say, how far is it from here to here? And you make a right triangle out of that. That's not a right triangle, right? That's curve. That curve is showing up. So these 2 points have to be really close. Well, if they're really close, then isn't this, in the language of calculus, a little bit of X, and isn't this a little bit of Y? And again, the D implies really little, like infinitely little. So then, what's that hypotenuse? Isn't that hypotenuse just equal to those terms squared, added together and square rooted? So then all we need to do is add them all up as it moves. So I'll just move it up to here. You may notice if you move it up to here, do you notice that dx is a lot smaller than dy now? Do you notice they're changing relationship? In other words, they're not exactly the same size. Down in the first one I drew, dx and dy look like they're about the same. They're about equal to each other, like I'm at a 45-degree angle. Whereas up here, dx is much shorter than dy. So the key is, well, add them all up. That's it. Now, the only problem is you should stare at that and say, I don't know what that means. Like, great, you wrote that down, but I don't know what to do with the square root of, like, I don't know what dx is. I don't know what dy is. I don't really know what to do with this. Now, here's the beauty of algebra. Could we do something with that that makes it look like something that we understand? So I want you to notice something, a couple of things. One of them is I stare at these two statements, and although I recognize them, I sort of find myself staring at them going, you know, huh? That doesn't really tell me what I need to do. And then also there's like we're used to seeing there being like a dx there or something. You know, so does that matter? Well, let me show you something beautiful. So although that's true, we're done. That's arc length. It's not very usable. So let's make it usable. Amazing what algebra can do. Watch this. This is brilliant. Who thinks of these things? Again, did I think this stuff up? No, somebody smarter than me did. And when I got shown it, it was like, oh my God, that's a brilliant idea. Who invented this stuff? I can imagine, if you will, the first person that invented this, or first person that decided to be interesting to know, you know, how long something travels. In my engineering classes, we talk about that a lot. Something moves along. A particle or something moves along some curve like this, and we're trying to understand how that motion works, and a big part of that is arc length, but I won't go down that road. So let's see what algebra can do with this statement right here. Watch this. If you took the square root of dx squared plus dy squared, and you multiplied it times dx over dx, which of course seems like, why would you do such a thing? But then I would like this dx on the bottom to go inside the radical. Again, you'll see why in just a second, but what do I have to do if I want it to go inside the radical? One of you tell me.
My initial reaction was raise it to the 1/2 power.
It's got to be this, you're going the right direction. In other words, it can't just fly in there for nothing, right?
You gotta multiply the root of it.
So if I left the top one out here, that bottom one can't just kind of fly inside. It could go in there, but what has to happen to it? I didn't look up it. I think Connor said that, but something has to happen to it, but he didn't quite have it exactly right. Just think numbers for a second. If I had like a 5 here and I had a 1/3 outside, can I put what has to happen to that 3 if it's going to come inside? I mean, you're used to going the other way. In other words, I'm sitting here and I have like the square root of 32. And so I break 32 down to 16 times 2. And then that 16 can come out from under the square root and become a 4, right?
Would it be 3 squared?
Yeah, to go this direction, don't you have to square it? Because it's going under a square root. So if I squared this, does it make sense? That would be okay then? If you think about square root of dx squared is dx, then it could come outside, right? You're just not used to going that way. Now, again, that looks like great. You just made it worse. It was already terrible and now it's worse. But watch what you can do with this statement. Well, notice you have junk divided by junk. And if you take dx squared divided by dx squared, isn't that equal to 1? And then if you take dy squared over dx squared, you may recognize that this now looks like something. And notice it's junk squared over junk squared, which means I could just write it as dy over dx and then sort of square it later. And there's a dx sitting outside. This is now a usable statement for arc length. And the reason is because what just went away is this, you should now recognize what this is. You've seen this before. What is that thing called? What's that animal called?
Derivative.
The derivative.
It is velocity in physics.
Yeah.
Yeah, velocity, rate of change. That's the derivative from last term. So this is what you'd see in your textbook. Well, let's just take a simple example to make sure we don't suck this up. Let's just take a parabola, y equals x squared. You know what those look like. Those are beautiful. We've been talking about this. Parabolas are always really simple. And I'm purposely not, adding, it's not x squared plus 3x minus 7. It's not a complicated parabola. It's just a nice simple parabola. And let's say we want to know how far is it from 1 out to, I don't know, 7. How far is it from there to there? What's the length of that curve from 1 to 7? Well, what do our directions tell us? We say, okay, well, if I go from 1 to 7, and I always take a square root because that's Pythagorean theorem, there's always a 1. And then what goes right there? There's always a squared. What goes inside that parenthesis?
The derivative of your equation.
Yeah, dy dx from last term. What's the derivative of x squared? The derivative of y with respect to x. What's the derivative of x squared?
2x.
2x. Done. Now, maybe you can take that integral. Like maybe you could do this by hand and actually get an exact answer. But do you understand what I mean when I say, in quotes, done? Can't even read my handwriting. Get rid of that. Done, in quotes, because we got technology to answer this question. Now, what I want to warn you about is because you're square rooting something squared, like even though this is the simplest equation I could think of to even write down, a parabola that has no extra garbage along with it, you can't take that integral. Like that integral is not takeable. You got the square root of junk. You might say, okay, well, all right, I'll make a little bit of progress. I'll say that's the same from 7 to 1 as the square root of 1 plus, well, 2x squared is 4x squared. That's a really hard integral to take, it turns out. I don't want to go down that road right now. You'll be able to do that when we get into chapter 8, but this is not an easy integral to take. Now, your book, and I sort of wish it wouldn't have done this. Your book works really hard to actually come up with problems where you can actually do this problem. Does it make sense that you need to be able to square root it? In other words, the problem with this problem is I've got junk inside of a square root sign, which is kind of a chain rule sort of a feel. Does that make sense? And so you might think, oh, substitution, I'll let u be 4x squared, or I'll let u be 1 plus 4x squared. But that is not going to get you out of the woods here. You may have noticed in the bead project that you had something like this, except there was an extra x out here, which is actually wonderful, because now if you let u be 4x squared, that x will end up canceling out. But the fact that it's missing in this problem is actually terrible. This is a really hard integral. For you right now, this is impossible. I'm saying quotes because it's not impossible. I could teach you how to do it. But you got to make a really creative substitution here. In the end, you got to let x, you got to let x be like sine of x. You got to let x be sine of theta, something like that. I spent a bunch of extra time on an extra credit problem with Cheyenne. She probably has at least a sense like, ah, that is doable. But you tell us, Cheyenne, how terrible was that?
It's bad.
It's bad. It's ugly. She probably regrets doing it. So if I was making up my own questions, I would just say, write the integral out and then use technology to answer the question. But just for the fun of it, let's do something logical here for a second before we cheat. Since we went from 1 to 7, of course, you would agree that that's a distance of 6. And then if I plug these in, like if I plug 1 in, I get 1 for a y coordinate. If I plug 7 in, don't I get 49 for a y coordinate? So that means this is 48 tall. You agree that my right triangle is 6 by 48. So if I did Pythagorean theorem with 6 and 48, square root of 6 squared plus 48 squared, I get 48.37. You shouldn't be surprised that's barely bigger than 48, because 48 is a huge number and 6 is so tiny relative to it. So what does that tell you about the length of the green curve?
Sorry, I have a question.
Please, don't be sorry though.
Where did you get your 6 and 48 again? I think I missed.
Thank you for slowing down and asking questions. So we decided we wanted to know the length of this curve from x is 1 to x is 7. So I'm just thinking of a right triangle here. And I said, well, we went from 1 to 7. So if I subtract those, that's where the 6 came from. And then I plugged 1 and 7 into x to get the y coordinates. So I'd know how tall it was. So when I plugged a 1 in, 1 squared is 1. When I plug 7 in, 7 squared is 49. And so that means this is at a height of 49. That's at a height of 1. So if I subtracted 49 and 1, that's where I got 48.
Got it. Thank you so much.
Good. Now, again, you don't need to do any of this, but I'm just pointing out that straight hypotenuse distance would be 48.37. So what would you say that arc length, the curve, what do we know for sure about that curve then?
That it's bigger than 48.37.
Exactly, a little bigger than that, right? And I need a good graph to tell how much bigger, but at least we know it's greater than 48.37, and that's about the best we could do. But now let's just go in and cheat. I'm going to stick this in my graphing calculator just so I won't show it to you, but I'm just typing the square root of 1 plus 4x squared, and I'm graphing it. And remember, this is no longer the graph. Like when you do this on your calculator, you're getting the area under a curve. That's so weird visually. So I get this V-looking shape. Isn't that kind of weird? It's a V-looking shape. And I say, I'd like to know the area under that curve from 1 to 7. And it tells me using the TI that I got 48.479. Isn't that cool? Now, I wouldn't have been surprised. All I knew it was bigger than 48. I mean, it could have been 52. Like I had no clue. I'd have to draw a good graph of this to see, of the original equation to see it. But it is a little longer. Cool. I'm actually surprised how close it is. What does that tell you about the real graph? Well, it tells you that that part of the graph must be really straight. You know what I'm saying? It must not be curved a lot. It must be real straight through that section.
So the ability to do this math makes sense, but what do we use this for?
Yeah, and that's why I throw so many projects into my class. You know, why would you ever want to know that? And again, this is the difference between a true mathematician and sort of a practical person. True mathematician says, who cares? I can find the length of any curve I want. That's awesome. A more practical person like me says, why would anybody ever want to do this? You know, I want to see some applications for this. Why would I want to do it? And I even have some trouble with physics where they, you know, they give some curve like this and they, you know, talk about a particle flying along in that shape right there. And you know, but I was just thinking, well, when do particles do that? Or why would I want to watch a particle do that? And why would I ever want to know its distance? And so tomorrow's problem will be an application for that. So.
Yeah, also in physics, most of the time when a graph looks like that, it's not really like a representation of it moved this way. It's more like time and space.
True. Just to cement the concept in, let's just do a couple other examples. And I will tell you, like on my test, I'm just going to say, set the dumb thing up. In other words, I really don't want you to take the integral. I want you to set the thing up, and I'll probably ask you to, you know, give the decimal answer, but the issue, the focus here will just be setting it up. And it's not hard to set it up at all. Let's see, let's try something. I don't know, sine of x plus 2. That might be a fun one, right? Do you remember what the plus 2 does to sine of x? Let's just draw a rough graph of it. What's the sine of?
It makes it go up y by 2 positions.
Yeah, so normally sine is like down here doing this, but then this is saying now move it up, and now it's going to do it along that. So it'll be something like this. It's this curve along here.
Because if you took the sine out, it would just be y equals 2.
That's right, y equals 2, which moves it up 2. Anybody off the top of their head, and I have no thought in my mind when I say this, but can anybody think of a reason why anything would move like that? Is there anything like a car? Does a car drive that way? Does something move that way where I'd want to know how far it was, so to speak?
Waves do. I mean, that's what I think of, like the ocean.
Yeah, if you're on a jet ski or something.
Ocean waves do that. So if I was traveling along something that was doing that, you know, maybe
like light.
Yeah, light supposedly kind of is modeled by something that works that way.
Or like sound that started at a certain volume, you know, rather than starting at just 0 volume.
Oh, it's like, why is there a weird noise in my house? I was gonna have to defend the fort. A random dog just came in. Does that ever happen at your house? Random dogs just walk in the door.
No, but at my old
we used to
house,
have
I had
random
random
goats.
tweaker.
If you leave it unlocked. My kids are here. Hi, dude. Say hi to everyone. You know, as a playful example, I'm always trying to talk about mountain bikes and stuff. And so, you know, I was on trails this weekend that had that shape. And so if you wanted to know, you know, how far did you actually roll? Again, that's very contrived because somebody would have to build a trail that was, you know, shaped like that. And, you know, why would you choose a sine wave? I mean, it's fun. That's why mountain bikes kind of do that sort of a thing. But anyway, let's put that off. So again, let's figure out, you know, that sine wave goes forever in both directions. And I could choose values that had pi in them just so that we kind of knew where we landed. But again, let's just choose random places. Let's go out, I don't know, out from 2 to 8. How far does that thing actually go? See if you can set that up. This is not a hard problem. And then we'll talk about, can we actually take that integrals or. Just make sure you're seeing this and seeing it as simple. So I've got a good drawing of it now. So we're going from here. To there. Notice in this case, I'm not going to be able to do what I did a minute ago, which is like draw some right triangle. Like last time that curve was straightish through there, but this time it makes no sense to kind of make an estimate for what that is. I only know that from x is 2 to x is 8 would be a distance of 6. And because this is getting there in some sort of a crazy curved fashion, the answer is more than 6, but 7, 8, I don't know. Well, this isn't hard. So if you say, I'm going to let this go from, I'm going to let these little tiny right triangles, these little hypotenuses slide from x is 2 to x is 8. Every single time it's the same. It's the square root of 1 plus, if you want to not screw this up, maybe you write that out every time. Like that part you're stuck with every single time. The only thing you got to do is take the derivative and throw it in there. Derivative of sine is cosine. The derivative of 2 is, well, nothing. Why would the 2 make no difference? Like, huh? I threw a 2 in there and it did nothing.
Isn't the derivative of that 2 0?
Yeah.
Is it,
So it seems to have no effect. It's like it could have came back in here and put a 20 in and it wouldn't have made any difference. Why does that not figure into the arc length? Since the derivative is 0.
It doesn't extend or move the length itself. It just moves the graph up or down on the y-axis.
Yeah, think about it. It makes sense, doesn't it? Because if you moved it up, is it going to change the arc length if you moved it up? No. So I guess it doesn't make sense. So in a sense, I threw the +2 in there thinking I was doing something. Didn't really make any difference. Now, again, we're faced with the question, can I take this integral? Is it an integral that I can take? You might be thinking, isn't sine squared plus cosine squared equals 1?
yeah, you can do that by substitution, right?
Notice if you subtract
Oh,
cosine over to the other side, it's not plus, it's minus. So it's like, that didn't help. It's not true. If that had been a plus sign, this would have been a plus sign. Then we could have switched it out for sine squared, the square root of sine, square root of sine, and we've been able to take the integral. In other words, you have to be able to take the square root of it. And your book is going to come up with these just weird looking questions where you actually can take the square root of it and get rid of that square root. But we need that square root to go away, and it's not going away in this case. And so once again, I'm just making this problem up randomly, but once again, this is hard. Like I have had a lot of experience teaching this class, and I'm gonna have to think about that. Like I'm making these problems up randomly. I'm not sure. Like that's a damaging thing. Notice it's really easy to write the dumb thing down as long as you understand what the format is. And in my opinion, for practical problems, you're done. Because do I need the exact length in a practical sense? No, approximate length will do. So bust out your calculator, ask it the answer. You're done. So I'm just going to quickly do that. Cosine of x. That's not super easy to type in.
Just out of curiosity, couldn't we still find this if we were to do negative sign, but just switch the limits? because a negative sign would equal negative cosine, which then you could do the 1 minus cosine squared. But we just moved the limits so we have the same like wave portions, I guess.
Yeah, in other words, the Eve is asking is, could I, and actually I'm still not sure I understand your thought exactly, but she's just saying, could I move it somewhere else? Since the fact is this could sort of be anywhere. Could I move it somewhere else where I'd maybe end up with 1 minus cosine squared and then I'd be able to replace it? The answer is, yeah, maybe you can. And again, true mathematicians go, they spend forever sort of trying to solve that, which I think is cool. I get that from a theoretical perspective, could you actually get this length? I think it's a terrific question. Again, what's fascinating about this is when you type that in your calculator, remember you're getting the area under a curve. That's so weird. We're calling it an arc length, but it's actually giving us an area under a curve. Such a weird thing.
Maybe I'm wrong. I think Eve meant like in the beginning, instead of, I think the original problem was with a sine x, but if the original was written with like a negative sine x, could we use that substitution?
Yeah, and then it would flip upside down.
Yeah, that's what I was saying. And then
The
if
problem
you move
is
the limit,
the derivative of negative sine of x is negative cosine of x, but what happens when you square negative cosine of x?
I'm gonna guess bad things.
it gets positive.
It turns into positive again. So your idea doesn't immediately work, but that's what mathematicians do. Like I'm curious about this right now too. If I was done with this class and I had nothing else to do with the rest of the day, that's the first thing I would do is say, I wonder if there is some way I could do this, and I'd play around with it for 2 hours. And that's a separate question, but I can cheat, and my calculator says approximately, because I have to round it off, 7.345. Can you agree that that looks reasonable? Since this distance here is 6, that it'd be more than 6? I would have thought it was reasonable. I would not have thought it was reasonable at 6.2. Do you agree with that? It's way longer than a straight line. We're getting there in a very circuitous way here. So it's not like last time. It's not really close to straight. If it came out like 12, I'd be like, that's not 12. So that looks pretty reasonable. But I'm just saying, make sure you separate out. I can write out the formula, I can cheat it to get an answer. Second is, do I know calculus enough that I could actually take that integral and get it exactly right myself? Fun too. Not hard to set up. So the key is you've got to be able to take the square root. That's the problem. And by the way, just in case any of you are thinking this, make sure you note that the square root of a squared plus b squared is not equal to a plus b. I wish you could square root those separately. I wish I could do that. Just say, oh, the square root of 1 plus cosine squared is 1 plus cosine. I just square rooted both of them. But that's screwing up the order of operations. So you can't do that.
Got an algebra question.
Go ahead.
If I put a negative in front of the square root, can I just distribute that in front of everything else inside of the square root? Or is that a...
You can, because, well, let me think about that. Can you? I was going to say you could bring it inside, distribute it inside, but remember to come in, it's got to be squared, which turns it into positive. So now all of a sudden.
Okay. All right.
So let's just do, I don't know, one more quick example, since there is a logarithm question in your book. Making that up. But let's find the arc length of that curve. Notice it's really confusing because it's a parabola, but then you're taking the natural log of the parabola. I have no idea what that graph looks like. I'm gonna go find out. but you're just reminding yourself, because notice you have to know how to take a derivative again. Like this whole section depends on taking derivatives of crazy statements. So it's like you got to dredge up all your knowledge that you had from last term. Natural log of x squared plus 6x. And again, this, now that I look at the graph, I notice, hey, can't put negative numbers in here, the graph, so I can't say how far is it from x is -2 to x is 7 or something, because it only exists in the positive values. And I'm a little scared saying from 0 to something, because notice it goes down forever. So it feels like if I said from 0 to 2, the answer would be infinity. So I don't want to get 0 in there, that'd be dangerous. But 1 to 5 seems reasonable. So let's do it from 1 to 5. Elise, you're good. What are you doing over here? Get on it. Notice this one is straight-ish through that section, so I probably could get a decent estimate of this if I wanted it, but I don't want to this time. Again, what happens every time before you even start the problem? You just say 1 plus the derivative squared. Every time it looks the same. But we're saying we're going from 5 to 1. How do you take the derivative? What's the formula? You should have a note sheet from last term. What's the derivative of natural log of junk?
Isn't it 1 over the junk?
1 over the junk. Oh, that stinks. It's supposed to be x squared, and I wrote x when I typed it in there. What an idiot. Dang it. Yeah. Oh, good. It's about the same. I don't have to change it. So the derivative of natural log of junk is, I'm going to say over here, dy dx. 1 over the junk times the derivative of the junk. That's chain rule. So it's 2x plus 6 over x squared plus 6x. Wow, that's nasty. Now, again, my gut reaction is I'm never going to be able to take the derivative of this. And so I'm just going to cheat and answer the question. Great.
Did you mean integral?
I'm an integral, yes. I'm never going to be able to take the integral of this, but I want to warn you, the book is going to ask you to, it'll ask you separately and say, it'll say, take that statement right there and simplify it. And amazingly, they will have made up a problem where you are going to be able to take the square root of it. So just for the sake of your algebra knowledge, I'm not going to quit quite so soon here, even though in my case, because I made this up randomly, I don't think it's going to go anywhere. But, well, let's see, I guess I can square those two things. I can take 2x plus 6 and square it, and I would get 4x squared plus 12x plus 12x plus 6 times 6. And I can take x squared plus 6x and square it. That'd be x to the 4th plus 6x times x squared. That's 6x cubed plus another 6x cubed plus 6x squared. So my square root statement then is 1 plus that. Am I done? Again, that looks like this is going nowhere. That's worse. That doesn't really help. It just makes it harder for me to type in. But you can add these two. What do you have to do to add these two?
Give them a common denominator.
Yeah, I can multiply the one top and bottom by the x to the fourth statement. So wouldn't that be that giant disaster? Which again, even looks more pointless, wouldn't you agree? But at least I can add them now. They have a common denominator, so my denominator on the bottom is the same, but now I can add what's on top. So let's see, are there any like terms up there? I've got an x to the fourth. I've got a 12x cubed. I don't have any more of those. 36x squared though, and 4x squared. I can add those and get 40x squared. And then there's a 24x and a 36. So like that's going nowhere. So in order to be able to take the square root of that, I'd have to be able to factor that down. And that doesn't look like it's going to happen, but the book will have worked very hard so that you actually can proceed with this. Which to me seems like a waste of time. I wish I had a way to make my own problems up, because I would not. In our case, this is going nowhere. I really need to be able to take the square root of that statement. I can't. And so I just made it worse. This is not any better than it was before. So I'm left with, I guess I'll just have to stick that in the calculator and cheat. Cheating is the best thing I can do, or I'm gonna have to know a whole lot more about integral taking. So I'm very interested that you see the big picture of this, because I think books get this wrong. I think they spend way too much time giving you this super narrow set of problems where you can, in this case, you can actually take its integral. And that's left over because you got to appreciate how new it is that we have technology that will do this like this. For hundreds of years, people couldn't find the arc length of most things because they couldn't take the integral of them. And you can see why, a class like this would turn into, let's figure out how to take the integral of everything, just because you can't. I mean, this is a neat formula, but we couldn't even do it for a parabola without a ton of pain. How much less something as ridiculous as natural log of something kind of ugly. So I just want to make sure you understand that.
Yeah, thank you to the people that put hours and hours and days into developing this technology that we can use today.
Yeah, it is unbelievable. So just because I'd like to make sure you can do this, because I will ask this on the test, and I also think it's kind of cool that you can relate, that you can actually see that the answer at least makes some sense. So I'm going to go back and modify this. So if I say square root of, shoot, I was hoping I'd be able to do this. So I'm going to say 1 plus we said 2x plus 6, is this right? I just want to do this in Desmos this time.
but you still wind up with 5 shares instead of 3.
Say that again, you end up with what?
Sorry, my computer decided to turn off my screen and unmute. I'm not sure why.
Got it, no problem. So I think that's the right answer. Oops, that's not supposed to be squared. It's supposed to be square rooted. And I didn't square what was inside. This is a very circuitous way of typing it, but is that right now? I think it's right now. So rather than type square root, I just said all that junk to the 1/2 power. You okay with that?
Yeah, that makes sense.
X squared plus 6x. Except for that was, isn't this a 6? X. There, now I think it's right.
I believe when you originally typed it in, you forgot the square root, that you could have cut that whole statement and then typed in the square root and then inserted it underneath the square root if you wanted to.
Yeah, the problem is when I'm using this app on my iPad, I can't copy and paste stuff. I can't select it and copy and paste. So I kind of have to type it all, which is annoying. But
Oh yeah, that sounds really annoying.
so I'm stuck with that 4.556. Notice that at least makes some sense, although this graph isn't exactly right because I typed it in wrong. If we went from 1 to 5, from 1 to 5 would be 4. So that this is a little over 4. Makes sense, doesn't it? So all I'm saying is, like, at least look at that. At least look at the graph and kind of, based on how curvy the graph is, be able to estimate it. Honestly, I'm hoping, like, on the test, this is a freebie. This should be easy. Like, I'm not going to give you some ridiculous derivative to take. And as long as you can take a derivative and you have the formula either memorized or I give it to you, this is not hard stuff. Now, I want to show you one quick thing, sort of in preparation for the project tomorrow, that's related to this. And if I wasn't giving the project, this is kind of a cool application. So let's say I'm here, I don't know, 30 feet in the air. I'm on a cliff 30 feet in the air, and I'm going to throw this ball kind of off, and it's going to go land down here like this. So the ball's going to land like this. But I want to make this a little more realistic. What mathematicians do is they just give you an equation of a parabola, but it's like, imagine you're actually out there throwing that rock. How would you get the rock to follow some arbitrary parabola? Does that make sense? What do you actually have control over? If you're out there,
The angle you throw it and how fast that is.
yeah, you have control over the angle and the speed, basically. And so let's say you wanted this to land down here at like 62.0. So you're going to throw it off there. And so you set the speed to get it to land a certain place. And by the way, the project tomorrow is going to be shooting a basketball. So you know where you're shooting from, and then you got the rim over there that you want it to land at. So you sort of have a starting point, 0, 30, and you have an ending point that you want it to land at. And so you have to control the speed automatically, but you have two things you can control: the speed and the angle. So here's what I want to show you that's kind of neat. Let's say that you set this up. And I guess what I'd like you to, does it make sense that you could actually throw that along a number of paths and get it to hit that spot? I mean, let's just say you're throwing it at a, throwing a rock at a bottle or something that's down there and you're trying to hit it. I was with like 30 guys in Mexico once, and there was a bottle down there like this, and we stood there for like 30 minutes trying to break it from way up high until somebody finally hit it. But does it make sense that you could actually throw it really high and get it to come down and hit it, or you could throw it a lot more directly and get it to come down there too? So that angle is kind of your choice. That's kind of the idea. So let's just pick, I don't know, 32 degrees. Let's say you decided to throw it at 32 degrees. Even that is kind of weird, right? Because it's not like you get a protractor out. But this is just a really cool application, because in the end now, the question is, what's this equation? Because if I have that equation, then I would have the ability to find arc length. I could find out how sort of far that rock flew through the air. But this is not an ordinary math problem, because you're being given things that you would actually have control over in this case. So I just want to show you some really cool things. So you would agree, I think, that the equation is y equals ax squared plus bx plus c, because it's a parabola. And you might even know that a is negative because it's kind of going downhill. Can you figure out any of those unknowns? Like, what can you figure out? Can you find A? Can you find B? Can you find C? Given that you have a couple of knowns, this, this. What can you
So that
find?
gives us an initial slope. It gives us the y-intercept, and we have the x-intercept, right?
Yep. So you got a y-intercept, you got an x-intercept. In a sense, 32 degrees gives you an initial slope, which is a great way of thinking of 32 degrees. It's actually a slope. So note the word that Vail just used, because we know a lot of things about slope. There's one that's relatively easy. Like, what does this one mean right here? What does that tell us for sure?
Y equals 30.
Yeah, y equals 30 when x is what?
0.
When x is 0. Plug that in. Y is 30 when x is 0. So notice x is 0 causes the b and the c to cancel out, and so c would have to be 30. And in the end, maybe you've memorized that from other places. Isn't c the y-intercept? Like, but you don't have to memorize that. Reason it out. So you actually know c is 30. Cool. But how are we going to get a and b? Well, this is even cooler. If you know why, and this is kind of what Vail said, and I'll make this kind of fast because I don't want to keep you guys longer, but isn't y prime, isn't the derivative of the equation a slope finder? Isn't that what derivatives do? They tell you slopes. And you can take, knowing that a and b are constants, you can take the derivative of ax squared. Isn't the derivative of ax squared 2ax, and isn't the derivative of bx just b? Isn't that the slope? And what you know, and first of all, do you understand that 32 degrees only applies at 0? In other words, that's the slope it leaves at, but isn't the slope changing like a billionth of a second later? So that slope is really only good. That 32 degrees is only good at x equals 0, isn't it? You got to be at that point for 32 degrees to be correct, don't you? And don't you know what the slope is there? Isn't slope equal to the tangent of 32 degrees? Slope is tangent is rise over run, isn't it? I mean, isn't there this little right triangle there that's 32 degrees? And this is the rise and this is the run. That's what slope is, right? Rise over run. So isn't tangent. And by the way, I mentioned that to you last term, but that's why somebody called that. That's why mathematicians call that a tangent line, because that the tangent is the slope of that angle right there. So since this is true at x equals 0, then couldn't I say that y prime is the tangent of 32, which equals 2ax plus b? But again, it's very important. That's only true when x is 0, right? So that means b is the tangent of 32. How are you going to get a?
Well, I mean, I guess since we know those other two values and we also know what y is, we can plug everything in and then just solve for a, right?
What other two values? I think I know what you mean, but just to make sure.
The tangent of 32 and 30, the b and the c, we know.
Yep. We now know those for sure. So what else do we know? What else do we know that we haven't used? We used the initial point. We used that.
We haven't used the x-intercept yet.
Yeah, we haven't used this, have we? We haven't used 62, 0. So maybe if I put 62 and 0 into that original equation up there, that would tell me what a is. We'll pick this up with the project tomorrow. Ultimately, tomorrow's project has to do with it's one of the neatest problems I've ever made up, in my opinion. Like 2 or 3 of them that I think are some of the coolest things I've ever encountered. And so I'll introduce that a little bit more tomorrow. But this is a reason for arc length. I don't know if it makes sense to you, but you would not want to shoot. If you're shooting a basket, why does nobody ever take the ball and throw it like clear to the ceiling and then come back down? Why don't they do that?
It would take way too much effort.
Hard. But your chances of making a basket are tiny if you throw it really high. They're tiny. I want you to think about that. They're also tiny if you throw it really low. If you throw it like at a 2-degree angle, all it's going to do is hit the front of the rim and bounce off. Like it has no chance of going in. You have to shoot it at somewhat of an angle, but you can't shoot it at 80 degrees and have it fly clear up to the ceiling, even if you're physically strong enough to throw it that high. There's a happy medium in there, and calculus actually answers this question. Turns out, and I don't think it's because of calculus, but it turns out the best shooters in the NBA are the ones that shoot at the correct angle. But they probably made it to the NBA just because they shot at that angle. It wasn't because they took calculus. But there are people that are terrible shots. You don't see him in the NBA too much, but Shaq was one. He's retired now, but he was a terrible free throw shooter. He shot like 40% from the line or 49% or something. But he was a big guy, like 7'2", and so he made his money just dunking on the inside, and he weighed over 300 pounds, so he just pushed people around and dunked. And so the fact that he couldn't shoot free throws was acceptable, if you will. But most people don't make it to the NBA being that terrible at it. But anyway, project is kind of related to that concept. I'd encourage you to finish this quickly when you leave, see if you can figure out what A is, and then graph it on the graphing calculator and see, does it actually go through the point 030? Does it look like it leaves at a 32-degree angle? If you take the tangent of that statement, do you actually get 32 degrees? And then does it land down there at 62, 0? And it's like, oh my God, it works. It's amazing. So we'll pick it up there tomorrow. All right. Get yourselves out of here. Stay after if you want to ask other questions.